Hello. So what I'm going to do, I'm going to talk about the notion of the arclant on section 7.4. Sometimes in some calculus book, they talk about this notion later when we have more technique of integrations. But in your book, they talk about it right at the beginning of this chapter 7. So we are going to do the same thing. Later on, we are going to get back to this one at the end of the course, when we are going to consider the polar coordinate, then the notion of the arc length would be very interesting over there. And of course, it's going to be used in calculus 3. There is going to be a special integral that we're going to define, and we're going to call it the line integral. And in case of the line integral, you do need the arc length. Okay, so what is going to be the arc length? Let's suppose we have a nice function. Okay, suppose f is a continuous function. So suppose f is going to be is a continuous function. It's going to be a continuous function on the closed interval a and b, with the condition that the derivative is, it's differentiable, and derivative also is continuous. So such that f prime, okay, f prime is also continuous. It's going to be continuous on this interval again. And sometimes we assume that f prime is not equal to the 0. Okay, sometimes we refer to this one. Okay, sometimes we say that in this case, the curve, the graph of y equal to the f of x is going to be called, okay, it's going to be called a smooth curve. A smooth curve on this interval. The notion of the smooth is going to be used much more when we get to the line integral, not of course in this course. Okay, and when we get to the notion of the polar coordinate. So what we are going to do is, so this is a situation that we're going to have. You see that is going to be, you have a nice curve. This is going to be a nice curve. So this function is continuous. So this is going to be, for example, this is going to be a and the b, and this is the graph, which is going to be y equal to the f of x. So what we'd like to do is would like to, suppose this is going to be your starting point, and you're going to travel along this, okay, travel along this curve. If you travel along this curve, so you would like to know what's going to be the distance that you have to go from this point. For example, we call this point A, and this is going to be the point B. So the distance along the curve is going to be your arc length. So we are going to find the length of the curve. For example, it's going to be the length, and we would like to take it from A to B. This is going to be the arc length to be able to do it. You know that if you want to do the distance, if you want to find the distance between 2 points, if these 2 points are going to be on the straight line, so we can use the distance formula to find it. Okay, we can use the distance formula to find the distance from the point A to the point B. But when it's going to be curvilinear, it's not going to be possible to do it, but this is calculus. So what we can do is we can estimate it. Since we are able to do it if this is going to be just a straight line, so what we're going to do, we are going to approximate this one, approximate this curve by kind of the polygon. So the way we can do it is we can partition this interval, okay, partition it into different segments, okay, and then if you connect them together, okay, if you connect these, so that would be the case, like in the case of the integrations. So if you partition it, this is the A and the B that you got over there. Okay, this is going to be the A and the B. So we can call this one x0, then we get to the x1, then we get to the x2, x3, and then we continue up to the xn. So it depends. You may partition it, divide into 5 parts, 10 parts, etc. So each of these parts would would create a segment, a line segment. You see, we get the line segment of here. So you may call this a starting point, call it P0. Then we go to the P1. Then you can continue, see, go into the another point, then continue, just keep going to get to the end. So in this format, what we are going to have, we're going to have a collection of points that give you this segment over here. Okay, so we get a collection of points. Let's say the segment that we're going to have, you see this is going to be P0, P1. Okay, this is going to be one segment, then we get a P1, a P2, and then you just continue. Okay, you continue to get to the Pn minus 1 and the Pn. Okay, so what we are going to do, we are going to find the distance, okay, the length of each segment over here. And if we add them together, that give you the length of the polygon here. But then we can estimate the arc length by this portion, okay? So I'm going to pick one of these points arbitrary. Okay, suppose we have one segment. Okay, if we pick this segment to be, you see, if this is going to be one of them, now suppose this is going to be pi minus 1 and the pi, and I want to find the distance between these 2 points. So the pi minus 1 is going to be the point that, okay, you get a point, you have the x coordinate, we call it xi minus 1, okay, and you drop it into the function to get the y coordinate. Okay, you can call it yi minus 1. Okay, then we get to the pi would be xi and yi. Okay, then this I can be go from 1, 2, 3 up to the end. Okay, remember the yi minus 1 is going to be f of xi minus 1, and the yi would be equal to the f of xi. Okay, it's just the x and the y coordinate of these points. This point is going to be the point, and the x coordinate is just the partition point that you get from here, and you drop it back into the function that give you the y coordinates. Okay, so if you want to find the distance between the segment, the length, and the length of the pi minus 1 and the pi is going to be equal to, we're going to use the distance formula. Remember the distance formula from algebra, it's going to be a difference between the x numbers, so it's going to be xi minus 1 all squared plus yi minus 1 all squared. Okay, so that gave you the 1. If you like, this is, you can write it down in differential form. It's going to be change in x, change in y. If you like, you can rewrite it as it's kind of a delta x or delta xi in this case, all squared plus delta yi squared. Okay, so that gives you the distance of one segment. Now the arc length is the one that you are going to add all these together and then you estimate it. So your arc length is going to be, okay, so the arc length is going to be approximate. Of course, this is going to be an estimate. If you want to have a better estimate, so what you can do is you can add more partition points, okay? If you add more partition points, then you are going to have a better estimate. But eventually, your arc length is going to be, let's say, limit. Okay, the best estimate that will happen if the number of the points would be very large or goes to infinity, if you like. So it's going to be limit of the sigma of this arc of this segment pi minus 1 pi I from 1 to n when n goes to infinity. Okay, so we just pick some partition. Some people may divide into 5 parts, 10 parts, 100 parts, but if you increase the number of the partition, you are going to get a better estimate. Okay, so this is it. If you substitute it here, so your arc length is going to be what? It's going to be the limit of n goes to infinity, and you have something like a delta xi over here, a squared plus a delta yi squared, when that's it, sigma, of course, limit of the sigma I from 1 to n. So what we are going to do, we are going to connect it to the integral. In order to get to this connection, we are going to focus on this part. You see this part? This part is going to be f of xi minus 1 minus f of xi. So we would like to connect this one into this delta x that you have over here. So it's a secret that anything, if you want to do something interesting or anything important in mathematics or in calculus, you have to go through the mean value theorem. And this is one of the earliest application of the mean value theorem. Remember the mean value theorem? If f is going to be defined on the closed interval of like xi minus 1 and xi, there was a c's, remember, such that f of b minus f of a equal to the f prime of c times b minus a. So I'm going to use that one. Okay, so this is it by the mean value theorem. Okay, mean value theorem. In calculus 1, we refer to it as MVT. Okay, MVT, this is it. There is going to be of course, for the function, okay, for the function f on each of these closed interval, xi minus 1 and xi, okay, there is there is a point, okay, there is a number. We used to call it c, we call it ci, because we can do it for each of these interval. There's going to be a number ci inside, okay, inside this interval, xi minus 1 and xi, such that now the statement of the mean value theorem, such that f of xi minus f of xi minus 1 is equal to the f of ci times xi minus xi minus 1. Okay, f of b minus f of a equal to the f prime of c. Of course, this is f prime. F prime of c times b minus a. Now, as you can see, this is the change in y that you got over here. So it's going to be delta yi equal to you get f prime of ci times it by delta xi. It can be done for every I. So this is it. So what I'm going to do, I'm going to take this one and I substitute here. Then I work on it to get a new formula for your arc length. Okay, so I'm trying to prove the formula for you. So I can write the formula right away. It's better to check it at the end of the theorem, the result. You get a formula and then you can apply the formula in order to get it. But since we are going to do this type of ideas in the polar coordinates again, so that's why we are going to explain it, okay? So I'm going to go and substitute here or here for the delta yi, and that gives us a nice formula, and then we change it to the integral form. So what I'm going to do is I'm going to substitute it here, okay, in the formula. So this is it, L, the arc length. I repeat it again, the arc length was the limit of okay, the limit of sigma of the square root of delta xi squared plus delta yi squared, okay, I from 1 to n goes to infinity. So that is the formula. Now I'm going to substitute this from that mean value theorem that I got. So it's going to be limit of n goes to infinity, and that would be the sigma. Okay, that would be the sigma, and I have the square root of delta xi as is. Okay, but this one we change it to the f prime of ci. Remember, it was f prime of ci delta xi, so it's going to be f prime of ci squared times delta xi squared. You see, that's it. I from 1 to n. Now I'm going to factor out delta xi squared, and then I take it out of the radical. So it's going to be limit of n goes to infinity. So that would be the sigma. Okay, I take out the delta x squared. So it's going to be delta xi squared. So the leftover is going to be 1 plus f prime. This is f prime, of course, from the mean value theorem. F prime of ci squared. Okay, f prime of ci squared. So if you take it out, so that gives it the limit of the sigma. This is I from 1 to n, I from 1 to n. So it's going to be the square root of 1 plus f prime of ci all squared. Outside of the radical, you are going to get your delta xi, I from 1 to infinity, n goes to infinity. That's it. You see what you got over here? You arrive at the Riemann sum. Your function f prime is continuous, so f prime squared is continuous. Inside the radical continuous, it's a 1 plus f prime squared is a positive, so everything is going to be a continuous function. Since it's a continuous function, this limit can be expressed by an integral. Remember, the way we are going to change it to the integral, a definite integral is integral from a to b. A to b, this would be our function, so a square root of, for the function is going to be 1 plus f prime of, instead of the c, we replace the c by x, all squared, and this delta xi would be changed to the differential of the x. Nice, you see? This is going to be the formula for the arc length. Nice result. Okay, so we are going to make it official. You know, we just proved it really. We proved it, but we can write down as a definition if you like. And this is going to be the arc length. Okay, so this is going to be the arc length of the graph of the curve y equal to the f of x. Okay, there are different ways to write this one. From, you can say from x equal to the a to x equal to the b, or you can say that from the point, okay, the point a with the coordinate of a, f of a, to the point, okay, to the point b with the coordinate of the b and f of b. Okay, so both of them are going to be the same thing. Okay, so this would be the conclusion for the formula for the arc length, but the condition that we talk about it, it's going to be satisfied to be able to do it. So what I did really, I just prove a theorem for you if you like. Okay, that give me the arc length. And this is, or just a definition, you can call it. So the conclusion is this: if f prime must be continuous, otherwise you cannot get the integrability here. Okay, so if f prime, the derivative of, you know that if a function is differentiable, there is no guarantee that the f prime is going to be continuous. Okay, because if it's going to be complex function, that's true, but not for the real valued function. So if f prime is continuous, is going to be continuous on the closed interval of a comma b, okay, then the length of the arc, or the arc length, okay, the length, that's it, the length of the curve of the graph, the curve of y equal to the f of x, okay, from as we talk about it, from a point, from point a f of a to the point b f of b is, that's it, is going to be the arc length. Sometimes they write a to b, and sometimes they leave it a, the point a, the point b, it doesn't matter, or just the a, it doesn't matter. Okay, so this is going to be the integral from a to b. We write L only, and this is it, is going to be 1 plus f prime of x all squared dx. This would be the arc length formula. So you have to memorize this formula. Since your book, they talk about it right early before integration by parts, so the examples are going to be very limited. But in future, we can have more examples, and sometimes this integral would be complicated, and you'll be able to find it by a calculator. But in our case, all the integration that we are going to give you are going to be can be done. So we don't need any calculator. But don't be surprised. Sometimes in your book, they may ask you to use a calculator to find this arc length. Okay, so we have a number of the very limited examples, and we give you one of them in this coming test, if you like, not on the quiz. Okay, so there are a kind of I should give you 3 types of problems. Okay, there are a group of them of this format. Okay, this is example. So our first example is this one. We want to find the arc length. Find the length of the curve, or arc length of the curve. This is it. The curve is y equal to, or f of x equal to the ln of x minus, the group of them are going to be of this format that I would like you to see it. And this is going to be the one when x is between 1 and 4. That's it. So you can graph it if you like, but we don't need it. So we would like to find the arc length on this interval, 1 and 4. Okay, all the conditions that we need are satisfied. The function is differentiable, f prime is continuous, so we go for it. We have the formula. Okay, so the solution is going to be, so the formula is the arc length. You have to find the integral from 1 to 4. Okay, the arc length, 1 plus, it's f prime of x. If you like, you can write it on y prime, it doesn't matter. So it's going to be y prime all squared and the dx. Okay, y prime or f prime doesn't matter. So we usually simplify this inside, outside of the integral, then we come back and we integrate it. So we go with the y prime first. Okay, that's it, the y prime, derivative of ln x would be 1 over x. And this is like 1/8 of x squared. So the derivative of x squared is going to be 2x over 8. And we simplify these two, so that would give us 1x minus x over 4. This is going to be y prime squared. So we are going to find the y prime squared. The y prime squared would be 1 over x minus x over 4 all squared. You can use the square of the binomial to expand it. Derivative of the first one is going to be 1 over x squared. Okay, minus twice of the first times second. 2 times 1 over x times x over 4 plus the square of a second one, which is x squared over 60. If you don't remember that formula, you can, you can foil it. But, it's easy to remember. So now that gives it a chance to simplify. This x and x would cancel out. These 2 and 4 cancel out. So the conclusion is going to be, you see, the conclusion is going to be 1 over x squared. Okay, 1 over x squared. And this is going to be minus 1/2. Okay, minus 1/2 plus x squared over 60. Okay, this is y prime squared. Now add 1. So what is going to be 1 plus y prime squared? You see, this is it. So you have 1 plus 1 over x squared minus 1/2 plus x squared over 60. Now we simplify the 1 minus 1/2 would be positive half. So that give you 1 over x squared plus positive half plus x squared over 60. There are a group of the problems like this one. Look at this. Compare it together. So when you get 1 over x minus x over 4 squared, this is the result. This one is exactly the same, but you get a positive here. So this is going to be 1 over x plus x over 4 squared. You see, there are a group of them of this format, so we would like you to see it. And that make it easy for you, because if you make a complete square, then this square would disappear and your result would be easy to find. Okay, at this level, most of them are going to be of this format. So take advantage of this. Okay, so the write down as 1 over x plus x over 4 squared. Okay, because you have two perfect squares. You see, this is the square of 1 over x, and this is the square of x over 4. And this is twice of the first times second. 2 times first times second. You simplify it. The previous one originally was negative. You get the negative 1/2. You have a positive 1/2, so we get a positive here. Okay, so this is going to be 1 plus. So be aware of this trick. Okay, that's it. Now if you take the square root, you see, if you take the square root, 1 plus y prime squared, so that give you 1 over x, x over 4 all squared. Everything inside is positive, so x is positive, x over 6 is positive. So this result would be 1 over x plus x over 4. You know that when you take the square root, you have to use absolute value. But since everything is positive, you don't need the absolute value. You see, the term inside the radical nicely simplified. So go back and form the arc length. So there you are. So L is equal to 1 to 4. 1 to 4, you substitute 1 over x plus x over 4 dx. Easy integral to find. Okay, so we go on. Integral of 1 over x is ln x, ln of the absolute value of x, but we find it between 1 and 4, so we don't need the absolute value plus. And this is like a quarter of x. So integral of x would be x squared over 2. So you have a kind of a quarter, then x squared over 2. Then you have to find it from 1 to 4. Okay, simplify it and then evaluate it. So it's going to be ln x, okay, ln x, and this is going to be x squared divided by 8, finding it from 1 to 4. Substitute, If you put the 4, so that give ln 4 plus 4 squared divided by 8 minus, open up the parentheses, replace the x by 1, so that give you ln 1 plus 1 8. Okay, that's it. Now ln 1 is 0. So the leftover is going to be, we have the ln 4 plus 4 squared would be 16. 16 divided by 8 would be 2 minus 1 8. Okay, just a little bit of common denominator, L4, ln of 4, so that give you 16. So that's going to be 8 common denominator. So that gives you 16 minus 1. So the result is going to be ln 4. Okay, and that's a 16 minus 1, which is going to be 15 8. So, you can use your calculator if you like to find find a decimal number for it, or you can leave it as is. Okay. So if you use your calculator, ln of 4 would be 2 ln 2. ln 2 is something like 0.69. You can get, you can get a number, but you don't have to. But, if you like, you can use a calculator. Okay, this is it. If I use this calculator to find it, but you don't have to. This is going to be ln 4. Then I'm going to add it to, okay, add it to, that would be 15 over, that's 15 over 4. 15 over 4. And the final answer would be something like 5 point. Okay, it's going to be 5.13. I think that's correct. Okay, you don't have to, but if you like to get this number, so L would be 5.13, and then with that. So at this level, this is the best case that we can have, because we cannot use a more complicated one, but when we get to the polar coordinate, we are going to see it. So this trick is very popular in most of the problems that you have in your book. You can use this idea to get it right away. And the one that you have in your practice test is going to be the same thing. Okay, so this is the first example. Now, for the second example, look at this formula that we have. You see in this formula, the function was given as y equal to the f of x, like the cases that you did for the, the area problem or the area between two curves. Sometimes they may switch the function, okay? If the function would be given to you in terms of the y, then you have to integrate respect to the y here. So I just give you one note for that, okay? Sometimes it's useful to know each direction are going to have, okay? So I give you the remark. If you switch the function, not a big deal. We can do it. So if the information of your function is going to be this one, okay, if that's it, if the function, if you like, if the function, you see x equal to the g of y, g of y is going to be differentiable on the interval is going to be something like c and d, and g prime is also continuous. Is going to be continuous respect to the y, of course. Then the arc length, or the length of the arc, okay, the length of the curve, the length of the curve. So your curve is going to be g equal to the x equal to the g of y, is given by, okay, it's going to be given by this one. See, the arc length is going to be equal to the integral of c to d, and the square root of 1 plus g prime of y all squared. But you have to integrate respect to the y. Okay, so if function is given to in terms of the x, you integrate respect to the x. If it's given to in terms of the y, you integrate respect to the y. It's the same thing that we did for the volume and for the area. Okay, so I give you one example of this type. Okay, so this is going to be the example that we are going to have for this one. This is probably in your book. Okay, you have a couple of them in your book of this format. So we'd like to find the find the length of the arc or length of the curve, find the arc length or the length of the curve. Now curve is this one. You see the curve is given to you in this format, x equal to the 2/3, okay, 2/3 of the y minus 1 to the 3/2. And then they give you y this time, when y is between 2 and 5. You see? Of course, you can change it if you like. You can, okay, this is y to the 3/2. You can raise both sides to the power of the 2/3 and find the y, but you better leave it as is. So you realize that your integration is going to be, you are going to integrate respect to the y this time. Okay, so the solution is going to be, so your formula would be L equal to integral from 2 to 5. You see 2 to 5. And this is going to be the square root of, okay, the square root of 1 plus, instead of the y prime, if you like, it's going to be x prime or the g of x prime. It doesn't matter. Okay, so it's going to be g prime of, that's going to be g prime of y all squared, but dy. Okay, so this is going to be your g of y. This is going to be your g of y. So your g of y is the 2/3 times y minus 1 to the 3/2. Okay, so the integral, you integrating respect to the y. As we did it for the other one, we find the g prime first. Okay, so it's going to be g prime of y this time. 2/3 is just a number, you keep it, you bring the power down, which is going to be 3/2 times the y minus 1 to the 1 dot. This is 1.5. 1.5 minus 1 would be just 0.5, so that give you 1/2. Okay, you simplify, 3 and 3 would cancel out, 2 and 2 cancel out. So that give you g prime of y. Okay, g prime of y equal to the y minus 1 to the 1/2. Okay, that's g prime of y, you square it. G prime of y squared. So it's going to be y minus 1 to the 1/2, then squared. When you square it, you lose the 1/2 because this is a radical y minus 1. Okay, so g prime of y squared would be simply y minus 1. Okay, so that's going to be g prime of y squared. Add 1. So it's going to be 1 plus g prime of y squared. Okay, 1 plus g prime of y squared would be 1 plus y minus 1. These two would cancel out, that give you y. You see, easy one. So we take the square root. So that give you 1 plus g prime of y squared. And this is going to be simply a radical y. So you are going to integrate, you see, to get your arc length. This is your formula. So you simplify the inside. Inside happen to be only radical y. So you're simply integrating radical y, and we can find it right away. Okay. So that's why this is an advantage for this formula. Okay. So the arc length is going to be integral from 2 to 5. but the radical y dy. It's easy to integrate. So it's going to be integral from 2 to 5 y to the half and dy. Y to the half, you integrate it, that give y to the 3 halves. Over the 3 halves, no constant c, but you're going from 2 to 5. Okay, you change the 3 half. So this is it. L would be 2/3. Okay, 2/3 of the y to the 3 half. Okay, going from 2 to 5. You need to use your calculator, of course. So that gives you 2/3. 2/3 times 5 to the 3 half minus 2 to the 3 half. Okay, that's going to be the one. You can use your calculator to find it. You can switch it if you like, or you can leave it as is. So 5 to the 3 half would be what? This is a 1.5. So if you want to simplify that, just show you. But you can write it down as is and be accepted. You see, for example, 5 to the 3 half is going to be okay. So you have two choices. You can find the 5 cube first, then take the square root. Okay, so this is going to be the square root of 125, if you like. But 125 is 5 times 25. Okay, this is going to be 25 times 5. So radical 25 would be 5. You get 5 radical 5. You see, if you don't want to use your calculator. This is going to be the case. The same thing for the 2 to the 3 half. So it's going to be cube root of 8, because 2 cube is 8. So 8 is 4 times 2. So that would be 2 radical 2. Okay, if you like this type of ideas. So the arc length is going to be 2/3, or you can use your calculator right away. That's a 5 radical 5 minus 2 radical 2. Okay, you can leave this one as is, or you can use, if you like, you can use your calculator to find it. Okay, so you can leave it, or if you don't like it as is, so we can find it. This is going to be 5. Where is my radical? So it's going to be 5 radical 5. Okay, 5 radical 5. And that's going to be minus, okay, 5 radical 5. Radical 5. Okay, this is going to be minus 2 radical 5, 2 radical 2. Okay, 2 radical 2. If you take this one, the result is going to be, okay, there's going to be something like 8.3. Then I multiply it by 2. Then I divide it by 3. So it's going to be almost 5.56. Okay, you can check it for yourself. But if you write down as is, we accept that. So it's going to be 5.56. 5.56 is going to be the arc length of your curve. Okay, you will see, if you take calculus 3, it's going to be used quite a lot. And if you want to work with the complex numbers or the complex functions, the arc length is around all the time. Such an important quantity. That's why we want to get to know it. Okay, we are going to use for the polar coordinate later, but again in calculus 2. Okay, so 2 different types of problems. You may have to integrate respect to the y, or it may integrate respect to the x. Now all the problems are straightforward, but you have only one in your book that seems to be easy problem, and it is easy, but you'll be surprised. There are 2 in your book. They seems to be very much like each other, but it's not going to be the case. Let me see if I can bring it and do that one for you too. Okay, so let me see what is that. Or otherwise, this is one of the problem that you have in your practice one. If I can, because there are two cases. Uh, one of them is the one that it takes a little bit time. Maybe I don't have it now. Okay, so let's see. I think that's it. That's the one. Let me try it. It's very similar to this one. Let's try to see if this is going to be the case. Okay, so example, this one is quite different, but it can be done. But there is a point that I would like you to see. This type of ideas are going to be using calculus tree as well. So we want to find this arc length. Okay, find the length of the of this curve of the curve. This is the curve. Y equal to the 3/2 x to the 2/3. Let's see. And this is going to be the case when x is going to be between 0 and 8. You see, that's the one. Let's try it to see what is the point about this one that I was talking about. Okay, so there are the function is given to function of x. So you write your formula and go for it. So the solution is going to be, so our arc length formula would be L, and this is going to be x 0 to 8. So it's going to be the square root of 1 plus y prime squared, but the dx, because we integrating respect to the x. Again, carefully take care of that y prime and come back. So what's going to be y prime? Y prime is equal to differentiate, that's a 3/2. You differentiate this one, you bring it down, so that give you what? That give you 2/3. Okay, that give you 2/3 x to the. Now that's the point. You see, 2/3 minus 1. 2/3 minus 1 would be negative 1/3. That would be negative 1/3. So this 3 and 3 would cancel out, 2 and 2 cancel out. So the result would be x to the negative 1/3. This is going to be our y prime. Okay, except the next step is square it. So y prime squared is going to be x to the negative 1/3 squared. So you know that when we get multiple power, we multiply them together. So that gives x to the negative 2/3. Okay, and then you have to add 1, and it's going to be 1 plus, okay, y prime squared, and that gives you 1 plus x to the negative 2/3. You see, that's going to be the case. Then you have to, okay, that's going to be the 1. And so eventually you are going to put it over here and then to integrate it. So you better simplify it a little bit more, otherwise you can't find that integral. So the simplification would be, I change this one into the positive power, 1 over x to the 2/3. Then I find the common denominator. So 1 plus y prime squared would be what? The bottom one would be x to the 2/3. Okay, the top one would be x to the 2/3 plus 1. Okay, that's the case. Now take the square root. So what's going to be the square root? The square root would be 1 plus y prime all squared. And you put the square root on the top and the bottom, you see? A square root on the top, that gives x to the 2/3 plus 1. and the square root on the bottom, x to the 2/3. Now on the top, you can't do anything about it. You have to write it down as is, x to the 2/3 plus 1. Down the bottom, when you take the square root, you see, you may think about it, this is like the x squared. If it's going to be x squared, you can pull it out of the radical. Okay, but there is a third over here. So this is okay. So if you take the square root, the result would be x to the 3rd. Okay, that's going to be the one. Because x to the 1/3 would be, this is just the square root, it's going to be 2. So okay, so it's going to be x to the 2/3 times 1/2. You see, this would be x to the 2/3. Okay, then the 1/2, then this 2 and 2 would cancel out. That give x to the 1/3. Okay, and you move it up, then you will find out this is going to be so useful. So it's going to be x to the negative 1/3. This is a special problem. You don't have many of these, but this is what it is. It seems to be very easy curve. It's not bad. Okay, so we get a radical 1 plus y prime squared. We simplify it as much as we can. Now we're going to find this integral. And then you realize that this integral, now that we simplify it, is going to be such an easy integral. Okay, and so that show you now how you continue with this type. So I'm going to get the integrations. So this is what I have now. Okay, so what I have, the integral of that function is going to be arclength. Okay, so what's going to be the arclength? So the arclength now is going to be integral from 0 to 8. Okay, whatever you have here, it's going to be x to the negative 1/3. Okay, the square root of 1 plus x to the 2/3 dx. You see, let's just check it. That is the case. Now you want to find this integral, you know that use substitution. You have to change this, okay, this radical. Check to see if you can do it with the new substitution. 0 to 8. Okay, this is going to be x to the negative 1/3. And then you have 1 plus x to the 2/3 times the dx. Of course, this is to the 1/2. Then you are going to do the u substitution to get it. Okay, you take this one to be u, and then you can find it du. You can do it with a shortcut, but I'm going to do it in general form so that you can see it. So the u sub, so I take the u to be equal to the 1 plus x to the 2/3. Then I find the du is going to be 2/3 x to the 2/3 minus 1. 2/3 minus 1 would be negative 1/3, the dx. And as you can see it here. So I'm going to find the dx. So the dx is going to be equal to the what? Is equal to the du over 2/3 x to the negative 1/3. So I go back into the integral and I continue. So I'm going to check this one only. So it's going to be x to the negative 1/3, 1 plus x to the 2/3, 1/2 dx. If you substitute, so that gives you x to the negative 1/3 as is. This is going to be u to the 1/2. And for the dx, you have the du over 2/3 x to the negative 1/3. So these two would cancel out. And the 2/3, you flip it, that give you equal to integral of 3/2 of u to the 1/2 du. Okay, pull out the 3/2, 3/2 u to the 1/2 du. So it's going to be 3/2 u to the 3/2 over the 3/2. No constancy. I'm going to change it in a minute, then I go to the 0 h. So this is going to be 3/2. You flip this one, that give you 2/3. Okay. So that was the 2/3. I changed it to the 3/2. And in this case, this is going to be u to the 3/2. So everything would cancel out. So you arrive at the u to the 3/2. But u was 1 plus x to the 2/3. 1 plus x to the 2/3. Now to the 3/2. It's going to be evaluated from 0 to 8. Remember, the original integral was the case. So L is going to be equal to the, replace the x by 8. So it's going to be 1 plus 8 to the 2/3, then 3/2 minus 0. So that gives 1 plus 0 to the 3/2. If you simplify it, so that gives you 1 plus 8 to the 1/3 would be 2, 2 squared would be 4. To the 3/2 minus 1. Okay, 8 to the 1/3 would be cube root of 8, which is 2. So the result is going to be 5 to the 3/2 minus 1. Okay, 5 to the 3/2 minus 1. Again, you can use your calculator, or if you don't want, this is going to be 125 minus 5 is going to be 5 radical 5 minus 5. So the arc length is going to be equal to, you can leave it as is, or you can use your calculator to give us a nice result. So it's going to be 5 times a square root of 5. Okay. And then minus, I'm sorry, that's minus 1. Okay, that's a minus 1. So it's going to be minus 1. That's it. So the result is going to be 10.1, almost. 10.1 is going to be the arc length. Okay, that's only one example that's going to be different from the others in your book. The rest can be done easily. So that gives you the idea of the arc length. We are going to use it in future, as I talk about it quite a lot, but right at the end of the course, when we talk about the polar coordinates. When we get the polar coordinates, because in application problems, most of the function would be given to you in polar form. Then you have to find, most of the time you need to find the arc length of the polar equation, if you like, and this is where we are going to use the step. Okay, so we're done with the 7.4. We are not going to cover anything else from this chapter 7. So quickly we go to the 8 and we talk about the integration by parts. Okay, have a good one. Let me know if you have any question. Okay, bye-bye.